Hi, guys. So, this next unit is kinetics, and kinetics is the study of reaction rates, meaning we're looking at how fast or how slow a reaction occurs. So, to help reactions, I guess, go faster, we have to understand what makes particles react. And the collision theory actually explains that. So, in order for particles to react with each other, they have to collide with each other, they have to hit into each other. But not every collision leads to a reaction, it has to be an effective collision. And what that means is that two things have to happen. So when they collide, the particles, they have to have sufficient energy. Spelling sufficient wrong. Sufficient energy, meaning they need to hit really hard. And they also have to have proper orientation, meaning they have to hit head on. So, a way to help us remember these two factors, I like to think of a home run in baseball. So, to hit a home run, the ball has to hit the bat in the right spot. It has to hit like directly. If you hit like right underneath the ball or a little bit on top of the ball or on the side of the ball is going to fly off in some random direction, right? And you have to hit it hard. If you don't hit it hard enough, it's not going to go out of the park, right? So that's what we want to imagine when we imagine our particles having an effective collision. If they collide in any other way, they might not be able to react. Okay. So, as far as like factors affecting reaction rate, if we want to make a reaction go faster, we need to increase the amount of effective collisions. The more effective collisions there are, the faster the reaction rate will be. So, the first thing we can do is increase the temperature. So, I want you guys to think about particles. If I were to add heat, right, our particles are going to start moving faster. They're going to have more energy. So if they're moving faster, they're going to collide with each other more. So that's going to increase the number of collisions, which is why our reaction rate is going to increase. It's going to happen faster. Second thing I can do is increase concentration. Now, guys, as far as like how you know something's concentration, we're going to be looking at the molarity unit, capital M. So if you can think back to solutions, a higher number for molarity means you have more dissolved particles versus a lower number. So as far as a molecular explanation goes, if I have more of a concentration, that literally means that I have more particles. So imagine walking around the hallway in school during class. The hallway's empty, right? So what are the chances of you colliding with someone? Zero. But then think about you walking around the hallways during, between the bells. The hallways are filled with people. So what's the chances of you bumping into another person? They're pretty good. So it's the same thing with concentration. If there's more particles, there are going to be more collisions. And the more collisions that occur, the more likely that more of them are going to be effective ones, and we're going to have a reaction happening faster. Our third scenario here, guys, is about pressure. And it's important that you know that we can only change pressure, not that we can only change pressure, but pressure will only be a factor if the reactants are gases, because you can't really change the distance between solid and liquid particles, where gases have all that space in between them, that making them closer together or farther apart is really going to affect your number of collisions. So by increasing the pressure, I'm giving my particles less space. And if they have less space to move around in, of course they're going to collide more. And my reaction is going to go faster. Our fourth factor that can affect reaction rate is surface area, right? So I want you guys to picture and I'll show you something else in class that's going to help. But I want you to picture a sugar cube. And I'm not going to draw this cube in 3 dimensions. So let's say this cube has this sugar has 4 surfaces available. So particles are going to collide with it here, 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 and here. How can I increase the surface area of this cube? I can crush it up into pieces. So let's say I break this up into 4 smaller pieces. I'm increasing the surface area by making the particle size smaller. How did I increase the surface area? Now every single one of these smaller pieces has 4 sides available for collisions. So I went from having 4 sides available to having 16 sides available. These inside pieces don't have to wait anymore to collide with something because now they're exposed to the other reactant, right? So if there's more space available, we're going to have more collisions able to occur. And anytime I increase the collisions, I'm making my reaction go faster. I'm increasing the rate. A catalyst. So guys, a catalyst is an extra chemical that you add to the reaction. Typically, you'll see it written like this. So I'll have reactant plus reactant, arrow, and they'll turn into products. And usually we know there's a catalyst if it's written over the arrow. It'll either say catalyst or it'll specify what the chemical is. So it's kind of weird because you add this chemical to the reaction and it helps the reactants collide with each other, but it doesn't take part in the reaction itself. Like you're not gonna see it bond with anything that's going on here. It's not going to end up on the product side somehow. So what it does, what a catalyst does, is it takes your particles and it aligns the particles. So typically, when the particles collide, they have to hit with a lot of energy. What the catalyst does is it lines them up so perfectly that when they collide, it's okay if they didn't have a crazy amount of energy because they're lined up so perfectly. So you'll see aligns particles. You might see lowers activation energy. And that's exactly what I just said. They don't have to have as much energy because they're aligned so perfectly. Another way you'll see a catalyst described as far as like multiple choice goes, alternate pathway. So in a chemical reaction, our particles are moving around randomly. So the collisions are happening randomly. The catalyst kind of redirects my particles. So that's what that like alternate pathway means. It like moves them together on purpose. All of those things help the reaction go faster because it makes more effective collisions. Finally, guys, and this is something we can't control, the nature of the reactants. The reactants are what they are, and some reactants are better at reacting and react faster than others. So in general, ionic is faster than covalent. And if you have aqueous ionic reactants, that's going to happen super fast. So think about what happens when you take something ionic and dissolve it in water, like salt, versus when you take sugar and dissolve it in water. So I'm going to take NaCl versus C6H12O6. When I dissolve this in water versus when I dissolve this in water, what happens? My NaCl breaks up into ions, and my covalent compound, my sugar, stays one piece. Now, if you guys think about a chemical reaction, you have to break original bonds before those atoms can go and bond with something new, right? So you're breaking bonds to make new ones. In an ionic aqueous solution, the original bonds are already like broken. The ions are already separated from each other. So for them to go and combine with something new, it's going to happen quicker than in a sugar molecule where you still have to break these 6 C's, 12 H's, and 6 O's apart from each other before they can go and bond with something new. Okay, so as far as the molecular explanation goes, we can say ions are already separated in solution. Okay. I like to think of like, let's say you're interested in dating in someone, right? It's a lot easier to date that person if they're already single. If they're in a relationship and you have to break up that relationship before you can start dating that other person, which one of those scenarios is going to happen faster, right? So that's similar to our ionic stuff. All right, so that is it for today, guys. I'll give you a couple questions and we will talk next time I see you.